Okay, let's make sure my volume situation is good. Okay, can you hear me at home? Good job, awesome. Sorry I'm a little late. Yay, welcome to the last half week. 3 days of classes, 2 days of this class, and then Thanksgiving, and the final, and then we're all done. So I finished grading the take-home part of the second exam, and the grades split into sort of two groups. There was a group of students that did really well, got 34, 35, 36 points out of 36 points. And then there was a group that did much less well. So 18 points or less. And so the folks that did less well, you got another assignment this morning, which is giving you an opportunity to resubmit the exam and get some of the points back, because it was pretty serious point loss for that group of people. The folks that lost 1 point or 2 points, you're just done because you did really well, and we don't need to worry about having you retake things. But for the people that did poorly, and you get a second chance. So there's an assignment on Canvas that explains the details, but you get to turn it in a second time, and you can get some of the points that you lost back, because otherwise it's really going to be a mess. And I'm worried that there's a lot of stuff that people, I don't know, it's unclear to me actually how much of it was an understanding problem and how much of it was waiting until the last minute and then not having a chance to ask questions problem, or probably realistically some combination of the two. So the main thing I would like to do today, I would love to spend today answering questions. We've got the assignment from chapter 17 that people started playing with on Friday, and I'd love to take questions on that, but I'd also love to take questions on the exam. So if there are questions about different aspects of the exam, I would be more than happy to take those. So if there aren't questions, I can talk about other stuff, but I would prefer actually if we did questions, because I think that would be a better use of everybody's time. So does anybody have any questions that you would like to start off with? And given that we're coming up on the final, these could be questions about anything that's happened all semester long. So don't be shy. Excuse me. Come on, somebody ask questions. Otherwise, I'll just have to talk about stuff. And who wants me to talk about stuff? Seems like a terrible plan. Everything makes perfect sense to everybody. That'd be pretty cool, but I'm not sure I believe it. Going. Okay. Then I'm going to answer a question that somebody asked by email, and which I answered by email, but which I think is actually an interesting question that brings together a number of things that we've talked about. And is related to one of the questions on the assignment we started Friday. So, on the assignment, question. So, this was a student who had been going through just a bunch of exercises at the end of chapter 16 and trying a bunch of problems. Stumbled across something interesting and asked about it. And so one thing that I would point out is that it's a good idea to just do problems, right? You do better at this by practicing, same way you do better at playing the violin or doing the long jump by practicing. And this is one of these things where practicing is a good thing. And the problem that they practiced, well, one of many problems they practiced on, but the one the question came up on, was exercise 16.8, which is write a function to calculate a tip of 20%. And they did it a couple of different ways, and they got some results that they didn't expect. So I'm going to share Jess. Share. I'm going to talk about what happened and why it happened. Okay, so I should be sharing Jess. Yep. So actually, we'll look at just the first one for the moment. So they did it recursively. And I don't know, to be honest with you, if that was the book's intention, but it's an interesting idea. And I think that it's cool that that's what they chose to try out. So the book says to compute a 20% tip. So you're going to take in an argument, which is how much you're spending, and then your job is to compute a tip of 20%. And what they did here using recursion, which I thought was very clever, like, again, I'm not convinced this is what the book was after, but I think it's an interesting thing, and it led to an interesting question. So they first had a base case that said, well, if the amount you're spending is $100, then the tip is easy to compute. It's $20. Okay. So if you're having a fairly expensive night out, you spend $100, the tip is $20. That's not too bad. Otherwise, and now this really assumes that the is greater than 100. If you call this with less than 100, it's not going to work. We'll actually try that. Actually, that would be worth doing. But they're saying if you spend more than 100, then the tip is the tip on $1 less plus 20 cents. Because 20% of $1 is 20 cents. So if you spend $101, your tip is 20 cents plus the tip on $100. So you take off $1, add the 20% for that $1, and then do a recursive call on one less. Does that make sense? That's sort of a not entirely obvious thing to do, but I think, it works. It's a good idea. Like I said, I don't know that it's what the book intended, but it's an interesting idea. But this is something to ask questions about. Like, if this does not make sense, you should totally ask about it, because it is a somewhat unusual way to think about how we give tips. Zeke. Yes. So Zeke's question is, does this assume that the money is a whole number? It does. So in fact, this only works if is a whole number that is at least 100. If either of those things is not true, then we're in trouble. So if it's less than 100 or it's not a whole number, the problem is this will never be true. So if we had 100.5, for example, this would be false. We come down here, we subtract 1, we'd have 99.5. That would not equal 100. Then we'd have 98.5. That would not equal 100. We'd have 96.5. That would not equal 100. Or actually 97.5, I skipped one. Right? And we would never equal 100. And same if we started with something less than 100. If we started with 10, that would not, 10 would not be 100. Then we'd subtract 1, we'd be 9. 9 is not 100. Subtract 1, we'd have 8. 8 is not 100. Right? So we've got a problem here that this is not going to terminate if we have either a fractional amount or an amount less than 100. And we can see that if we try tip 1, let's say 120. Well, let's do tip 1, 127 first. Oh, look, it worked. It's kind of weird that it's got all these, instead of 0.40, we've got 0.3999998. That's actually where I'm headed with this, is to talk about that. But these other questions are really good, so let's talk about them for a second. Now, if I say, well, we've got $127.37, maximum recursion depth exceeded. So we called tip 1, called tip 1, called tip 1, called tip 1 so many times that it crashed and we got this error. So if you think about what needs to happen for something like a recursive call, like for this, speak English. If you think about what needs to happen for a recursive call like this to work, let's imagine I've been called with 127.37. I'm going to make a recursive call with 126.37. Let's say I hand that job to Joseph. Now I'm still sitting here waiting for Joseph to give me the answer back, and then I will add 0.2, and that will become the overall answer. So I have to still exist in some sense, waiting for Joseph to give me an answer back. Joseph has got 126.37. He makes a recursive call for 125.37. And let's say he hands that to Dongting. Now Joseph is waiting for Dongting to give him an answer before he can compute the answer and give that to me before I can compute my answer and finish the problem. Now Dongting makes a recursive call and he gives it to Darren. Dongting's still waiting. Darren hands it to Sophie. Darren's waiting on Sophie. Sophie gives it to Zeke. Sophie's waiting on Zeke, right? And so you have all these, and they've got a formal name. They're called stack frames. You don't really care. That's sort of a pay grade a little higher up the food chain. But they do have a name. They're called stack frames. And every one of these stack frames is waiting for the next stack frame in the line to give it an answer back. And it can't do its math and return an answer until that happens. Every stack frame takes a certain amount of memory. And there's only a finite amount of memory on the computer. And when the stack frames, well, there's a certain memory that is set aside for stack frames in the system. And again, the details are not what we care about right now, but there is a certain chunk of memory that's like, you are for stack frames. And that's got a fixed size. And when it says maximum recursion depth exceeded, what it's saying is that I ran out of stack space. I allocated stack frames over and over and over again until all of the space for stack frames was full. And then I couldn't do it anymore, so I quit. And so, you know, it's like I call and I pass it to Joseph, who passes it to Dongting, who passes it to Darren, who passes it to Sophie, who passes Zeke. At some point, the room's full of people standing around waiting for somebody to give them an answer. And once the room fills up, then the system tips over and you get an error message like this. So that's where this error message is coming from. And it's for exactly the reason you said, Zeke, that we have a fractional amount, we're never going to reach 100. And we get the same thing if we do anything less than 100. So even if we do a whole number less than 100, we're going to get maximum recursion depth exceeded. Okay. So that's a problem, and we should come back and fix that problem in a little while. Right now, I'm going to just pretend that it's okay, so that we can talk about the question that the student asked. Then we'll come back and fix this problem of whole numbers and being greater than 100. All right. So other questions about this definition before we go on to an alternative definition? Questions? Questions at home? Going. Okay, awesome. Then, okay, so the second version the student had, I don't know what they were thinking, but I think that you could read it as at least trying to deal with the less than 100 problem. Doesn't deal with the whole number problem, but it does deal with the less than 100 problem. And that version, instead of having 100 as the base case, uses 0 as the base case, which is probably more sensible. Using 100 as the base case means, you know, I can't go spend $10 and leave a tip. And actually, the last time in Morris that I spent $100 at a restaurant was never, that I can think of. I mean, it may have happened, because there probably was some time we had a big group of people. But I mean, realistically, you'd have to work at it to spend $100 at a restaurant in Morris. You'd have to be paying for quite a few people, or some people that were very, very hungry. So it would not be easy. So we would like a tipping algorithm that can handle more Morris-like amounts. And so what they've done is they've just said, oh, we don't have to stop at 100. We can stop at 0. And if the amount is being spent is 0, the tip is 0. If I'm not spending any money, I don't have a tip. And then the recursive case is exactly the same. We will add 2 cents or 20 cents for every dollar. So we'll subtract $1 here and add 20 cents and do the recursive call. Now that still doesn't handle the fractional amounts, but it does handle the amounts less than 100. It will fail for negative amounts, but you usually don't leave tips on negative amounts. So that's probably actually a pretty reasonable assumption. You know, that would be somehow the restaurant's giving you money and you're tipping on money. Yeah, so it doesn't make any sense to have a negative amount there. So this is actually pretty reasonable on the base case. This is a better choice, arguably, for a base case than this one. It still leaves us with the problem of non-whole number amounts, but we can do a tip for $57 and we get $11.40. But if we tip for $57.49, we get the stack depth exceeded problem again. So questions about tip 2 versus tip 1. Questions at home? Going. Okay. Now, what led to the student asking me a question was that tip 1 of $200 and tip 2 of $200 weren't the same value. And the student didn't understand why and wanted to know if I could help them figure out why those two things were different. Because it seemed like they ought to be the same. And they're different only by the tiniest of amounts, right? They are the same up to, that's probably like 10 decimal points. And then they're off by, you know, 0.004. And if we say 500, right, they're off by very, very small amounts, way off in the distance. So the student was like, why is that? You know, why are they so close but not quite the same? Anybody have any thoughts on why that might be? And it's totally okay if you don't, but I'm curious if anybody wants to like throw out a proposal. If we go back to tip, oh, I need to do tip 2 for that one. Go back to tip 2 of 57. This looks a little suspicious. It clearly ought to be $11.40. And we've got 0.99999999991. And this looks kind of like that problem. And I presume, and you should correct me if I'm over presuming, I presume that most of you have run into this issue of infinitely repeating decimals. This would have come up probably in some part of elementary or high school math somewhere. I don't know. It's been a long time since I was of that age, and I don't honestly remember where these things happen. And of course, they might happen in different places now because you've all had very different educational experiences than I probably had. But the problem is we cannot exactly represent 1/3 as a decimal fraction, as a finite decimal fraction. So we end up with an infinite fraction. So 0.3 repeating. And some repeating fractions are more complicated. 1/7 actually repeats a whole sequence of numbers instead of just a single digit. So 1/7 is 0.142857, 142857, 142857 forever. Okay, but it again does not have an exact finite decimal representation. Now, without getting too deep into the weeds, the same thing is true in binary. Remember that the computers are storing things in binary, not in decimal. So 0.2 is interesting because it has an exact decimal representation. So 1.0 divided by 5.0 has an exact decimal representation, 0.2. And that looks like everything's good. But in fact, there is no exact finite decimal representation in binary of 0.2. So in binary, 0.2 decimal is 0.0011, 0011, 0011, 0011, 0011 forever. And we could, you know, we could sit down and do the math for why that is, but I don't want to take that much time. We'd have to like explain fractional binary. The important thing is that it's true that this is the case. And actually, if you Google, you can find web pages that tell you how to convert decimals, fractional values from decimal to binary, and you would get exactly this. But the point is, we don't have an exact finite binary representation for 1/5 or 0.2. Even though we do decimal. And so the base you use can affect what kinds of values you can express exactly and what values you can't. If we did all this in base 3, we could actually express 1/3 exactly, but we still wouldn't be able to express 1/7 or 1/5, okay? So it's going to be a function of, the representation and the values that we want to represent, as to whether or not we can represent them exactly. But this is the key point, is that 0.2 is actually an inexact value in binary. And this student is adding 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.2 many, many, many times. And each of those 0.2s is a little bit off. And when those small errors accumulate through enough additions, it starts to add up. So if we do, let's say tip to 1, that looks good. Looks good. Oh. So when we add 0.2 to itself 3 times, that little error off in the wilderness starts to show up. And it was here in the earlier ones as well. Python was essentially suppressing it. It was so far down the road that Python was like, yeah, that probably is just like a rounding problem. And I'm just not gonna, I'll just round up and show you what you have. And it was willing to do that for 0.4 as well. But when it got to 3 of them, it's like, oh, that's a big enough error, I'll show it to you. And if we continue, right? Oh, there, weirdly enough, it actually jumped back. That may be because 4 is a power of 2, actually. And there, it's exact again. And there, it's exact again. And there, it's exact again. And now it's not. And that may blow up my power of 2 theory, because 8 to the power of 2 as well. So I'm not sure I'm in a position to say why it was exact there for a while and then hopped off again. But at some point, it'll just be off and stay off forever. There's some weird stuff happening in the early stages, but eventually it's going to just be wrong. So if we say map tip to range, I don't know, let's say 40, to get a whole bunch of values quickly so I'm not typing over and over again. So we're exact, we're exact, we're exact, we're not exact, we're exact for a little while, then we're not exact, then we're exact again for 2 more goes, and then we're not exact, and I think we'll never ever be exact again. I could be wrong. Maybe it sort of, comes back at some point. But the amount we're off varies a little over time. But it's also getting bigger. Like here, notice that the decimal point is in this position, but now it's over 1, which makes it a bigger error, right? It's closer to the decimal point. And here we've got 4 of whatever those things are. So that's now 10 times the error that we had here. This is 10 times the error that we had back at this point. So we are, I think, slowly increasing the amount of error. And if we, I don't know, let's go crazy. There's a whole bunch of them. So I'm guessing that these are going to be, yeah, so it looks like here we were at this position, and then we increased, and then we jumped over a position here. So the error increased again by another factor of 10, and it is increasing again in that position, and is up to 0.6 in that position, or 6 in this position. And if we kept going, presumably it would get bigger and bigger and bigger. So this is just because we are taking that little tiny error and we're compounding it by adding it to itself over and over again. And that small error compounded just gets bigger and bigger over time. And that's why that fundamentally gets us back to the question of why were tip 1 and tip 2 different. Tip 1 doesn't compound past 100. It stops at 100, whereas tip 2 stops at 0. So if we say tip 1 of 200 and tip 2 of 200, tip 2 added 100 more times than tip 1 did. And so the way its error compounded was different. It's a little odd that its error is smaller, to be honest with you. I would have expected it to be bigger. But again, this is behaving kind of oddly. And again, tip 1's error is slightly bigger, which I don't fully get why that would be. At some point, oh wow. So that would have succeeded. It's just that the maximum recursion depth isn't very big. It wouldn't let us go 900 deep, which is like, oh, that makes me sad. But that's why these are different, is the way we represent the numbers isn't exact. And by adding over and over and over again, we're going to get values that are not exact. And that error is going to compound. And because these terminate at different points, 100 in this case, 0 in this case, the amount of compounding is different, and so the errors are slightly different. And that's why the two numbers aren't the same. So we've got recursion, and we have the representation of numbers, and so a lot of cool things happening in this example, which is why I wanted to share it. Questions about this before we return to the question of how to deal with fractional amounts? Okay. So, how would we deal with fractional amounts? Both of these fail if we have a whole something that isn't a whole number. So if I were to say def tip 3 money, and here I want to with fractional amounts, what would be a way to deal with that? Anybody? Zeke. Ah, okay. And then so you're suggesting that this would be the same? Ah. Yeah, so this works, but as Zeke pointed out, and I don't know, people online probably can't hear this, but this sort of misses out on any amount that's between 0 and 1. We end up kind of throwing that away. So if we had this leaves out any fractional amount. So we go from like 375, tip 3 of 375 would be tip 3 of 275 plus 02. Tip 3 175 plus 02 plus 02. Tip 3 0.75 plus 0.2 plus 0.2 plus 0.2. Tip 3 negative 0.75 plus 0.2 plus 0.2. Oops. And then this would be 0 plus 0.8. So actually, notice that this doesn't actually leave out the fraction. It tips a whole 20%, a whole 20 cents for the fraction. So actually, this doesn't leave out the fraction. This tips, so let's say this tips a full 0.2 for any amount less than $1. Because when we had this here, this rewrote to this. So we gave them the whole 20% tip for only 75 cents. And if this had been 0.01, 1 penny, we would have left 20-cent tip for 1 penny at the end. So this over tips a hair, okay? But it does solve the problem of this should work for fractional amounts, okay? But it should work for fractional. Let's save it and load it and see if that's true. Tip 3. Hey, where's tip 2? Boom. Tip 1. Boom. So tip 3 is an improvement. Oh, and actually, if we do 3.01 to see that, you know, we leave a full 20 cents for that penny. Whereas if we do 3 exactly, then we almost have 60 cents with the weird error thing going on. So that does fix things. It isn't entirely exact, but it does come pretty close. Questions? Now, if we wanted to make it exact, we could say if 0 less than or equal to money less than 1, return 0.2 times money, else return tip 4 money minus 1 plus 0.2. Yeah. And now here I'm computing the exact tip for the fractional part instead of assuming it's 0 or 1 or 0.2 or something. Now tip 4 works, tip 3 0.1 is just a hair bigger, a little bigger. Whoa! Yeah, no, that's right. Got excited. Right? And so that does like actually completely solve the problem. But this also points out that we totally don't need recursion because this would have just been the answer anyway, right? We could just skip recursion altogether. And multiply by 0.2, and then we're done. And now we can do big amounts and it'll work because we don't run into stack problems because we're not recursing all the time. And weirdly, and I don't fully, I mean, I sort of get, but I only sort of get the, you don't get the errors. Oh, you do actually in some cases. So you do still get errors, even though you're doing multiplication. It turns out the errors end up in different places, and there are more instances where you don't have errors. And the errors don't accumulate because we're not repeatedly adding. You get a certain error when you do the multiplication, but you just get the error from that multiplication, not error compounding on top of error, compounding on top of error. So I think you'll find that the errors here are generally smaller. than the errors that you get with the recursive tipping algorithms. So yeah, I'm guessing that this is probably what the book was asking for, but I don't know. It's not completely clear to me what was in their head. But the others, you know, are totally cool. But yeah, once we get to here, it's kind of clear that, well, we don't really need recursion anymore because this really is the important piece. And let's just make a function out of that and be done with it. So recursion is a wonderful thing, but it is not the tool for everything. There are things that you want recursion for, and there are things where you're like, okay. And this is probably one of those. That was a lot. Questions about any of that? We got 20 minutes. Questions about anything? There ought to be questions. Questions about the exam? Questions about the homework? Questions about the final? Nothing. Okay, that's cool. Is there anything somebody would like me to just talk a little bit more about that might end up on the final? That you don't have like a question about it, but you know that it's like, that HTML stuff bugged me and I don't feel like I get it, or recursion just seems like magic and I don't get that, or it's been so long since we've done pictures. Can we look at another example of pictures? What would be something that you would be useful for me to do that would benefit you? Because you're the paying customers here, Pete.
I have a question.
Okay, that'd be great.
About the interval. I didn't understand what interval thing actually mean.
I'm not sure I'm understanding. What are we talking about here?
Interval.
Interval.
Maybe
Oh, iterable. Iterable. Yes, I get you. And can you remind us where is that in chapter 17? Or is that in chapter?
Actually, oh, I'm sorry. It's my arrow when I was programming.
So you got an error that talked about iterable?
Yeah.
Do you remember or have the actual code that generated that error?
Actually, I met this before and I couldn't find right now.
So I can say a little bit about what iterable is. I don't actually know the error that you're talking about. I'm not used to seeing an error in Python about iterables, but maybe, not sure. So when, Oh, maybe I might be able to make this work. If we say, I don't know, let's see what would be an example. Let's think about a little function sum. It takes a list of numbers and it loops over all of the numbers. And for every number, it adds that value to our result, our running total, and then it returns result. Okay. And so if we load that up, we should be able to say sum. Get 5 plus 8 plus 9 is 22. And if we say sum range, the sum of the first 20 natural numbers is apparently 190. Who knew? Okay. Now, I'm going to guess here, but I don't know for sure, that if I say sum of 7, I might get something about iterable. Ha ha! I did. Go me. So the problem here is I provided an int when this needed to be able to iterate over XS. So XS is 7 here. And a for loop requires this, the thing after n needs to be what Python and actually a lot of other programming languages calls iterable. What that means is it needs to be a list. It needs to be, or a string, right? It needs to be something we can iterate through. We can go down the sequence one at a time and get to the end. And it's a general idea because it includes both lists and strings. And in fact, as one, if you read chapter 17 and they talk about objects and inheritance, which we are not doing anything with in the assignment, but you can define your own object, your own class, and say that it is iterable. So you can make something that's iterable that isn't an array or a string if you know what you're doing. And this is sort of above the pay grade of this class, so I'm not going to go into the details. But you could have some kind of new object that is iterable. You could implement the right pieces and you could use it then in a for loop like this. So if you get an error that something is not iterable, it means you probably have something after the n in a for loop that isn't a list or a string. Okay. That would be my guess. And so that would be the thing to look for, is look for the thing after the n being something that we can't iterate over. Did that make sense, Juan? Did that help? Okay. And notice that here the fundamental problem isn't the iterable, it's that I passed the wrong type. Right? And this is, I think, probably 30, maybe 40% of the questions that I've received this semester, and this is not just about this semester, this is in, true, some version of this is true for every intro class I've ever taught. Some non-trivial percentage of the questions that I've received have come down to people passing the wrong type somewhere. So passing a number when it should have been a list of numbers, or a list of numbers when it should have been a single number, or a character when it should have been a string, or something like that. This is a very common problem. And so this is another version of that problem. So if you see that something is not iterable, there's a good chance, especially if the thing you're looping over is the argument to the function, there's a good chance that you just didn't pass the right kind of thing to the function. So yeah, that's totally awesome. And notice if I say, if I pass Morris, Morris will be iterable. So this line 47 will actually work. The problem is going to be here when I try to add 0 to M. It's going to be like, I don't know how to add 0 to M. And so we're going to get a type error again, but it's going to be on a different line, and it's going to say different things. Yep, the error was int and stir, inappropriate argument type, and an attempt was made to call a function with a parameter of invalid type. And so basically we called plus with an int here and a stir here, and plus didn't know how to add those two things together. So that's why that blew up. And they're both, in some ways, similar mistakes, right? In both cases, we're calling sum with the wrong kind of thing. Here we're calling it with a single number. Here we're calling it with a string, but we get rather different errors, okay, which can make it confusing to try to work out what's going on. Great question. Other questions? Or things you'd just like to see another example of? Great. So the final exam period is Tuesday from 4 to 6, just to get ahead a little bit on that. And so that's Tuesday, the 1st of December. So that's the Tuesday after Thanksgiving, from 4 to 6. I think there should be at least a small take-home part to the exam. As well, the bulk of it will be the in-class exam on Tuesday, but I think there should be a small take-home part to the exam. I'm a little torn about how to, basically when to hand it out. Because I could hand it out tomorrow and have it be due Tuesday. But then you're sort of, you feel like you ought to look at it over Thanksgiving. And I don't really want you to have to feel like you should be looking at an exam over Thanksgiving. That's not very nice. On the other hand, like if I assigned it Monday and then it was due Tuesday, that doesn't give you very long. And if I assign it Monday and it's due like Thursday, then maybe that overlaps other exams and you were hoping to have this thing be done and out of your way. So my inclination, and you can all yell at me and suggest alternatives, because I would love to hear from people. I don't know what your lives are like, and I don't know what would work best for you. But my inclination would be to hand the take-home exam out, sort of release it on Canvas Friday, so the day after Thanksgiving. So you get some time where you just don't have to think about this. But then you do have time to look at it over the weekend and ask questions if you're stuck. Because I think part of the problem with the take-home part on the previous exam is that people just didn't ask questions, waited too long. And I can set up some office hours times where you can sign up for question slots. And I can try to give people a hand online that way. So that's what I'm thinking, is handing out the exam on Friday. It'll be due Tuesday night. And I'll have some appointment slots. Certainly Monday and Tuesday. We could talk about having some appointment slots earlier, if that would be helpful, but I don't know how much people would use them. And I'll be looking at email and Slack, so you can use those to ask questions as well. So does anybody have any questions or concerns about that as a plan? Anybody have an alternative suggestion you'd like to share? Not hearing anything. I will take that as a, that'll do. And we'll go from there. Other questions, comments? Things I can help with?
I also have a question about the enumerate rate. Enumerate.
Okay. Does that
How-
also come up as an error, or is that something else?
No, I'm confused that how can we use it into our function? Use this concept.
So where did you run into enumerate? Is that in the book somewhere, or where did you see that?
It was you mentioned in the class.
Zeke also remembers me saying something about enumerate. Enumerate. I don't know. What? Is this a built-in function? Oh, yeah. Okay. Nope. Yeah. Okay. I think I know. So for, well, let's do this. For I in enumerate, enumerate 5, 8, 9, print I. Yeah, so enumerate is like using it. You would typically use enumerate in a for loop. You don't have to. You can use it in other places. And it, instead of just giving you the values, you get the position in the list and the value. And so that's right. That was important because there was a question. I think Nicholas asked a question way back when about if you had adjacent letters in a string, and we needed to be able to look at the things around an item in a string. And so you would use enumerate typically if you needed to care about the position of elements in an iterable value. If you don't care about the position, like in sum, we don't care about the position, then you wouldn't bother with it. But if the position mattered, then enumerate could be a useful thing. We've run out of time, but I can try to come up with an example of enumerate and post it on Canvas today. Let me make a note. Enumerate example. So I'll try to do that after class here, if that would be helpful. I don't think I would not expect enumerate to come up on the exam. The fact that I couldn't even remember what it was without help, clearly it's not like front of my mind as a crucial item of the course. So don't worry about enumerate if you're like, what the hell? But I will try to post an example of how we might use it. Totally good question. But don't sweat it. It's not going to be like a major issue in the class. So, oh, and I didn't share, I did an example of enumerate with Jess, and then I totally forgot to share the screen. So that's an example of what enumerate might look like in Jess. So, okay, I'll share all this. I'll let you folks go. Between now and Wednesday, like, think about questions that you like some help with. I'll actually probably post a little assignment on Canvas asking people to share some questions or things that they would like us to talk about on Wednesday, because I would rather, I can make up content, but I'd rather be answering questions for you folks. That's a better use of everybody's time. So thanks a lot, wonderful people. Stay safe. We'll talk to you again in a couple of days. Oh, and I have a bunch of appointment slots Tuesday, which nobody has signed up for. So if you've got questions and want to meet tomorrow, feel free to grab a slot.